Good afternoon friends and welcome to the EduSite Network. Our today's topic is part of our series on carboxylic acids, and today is in fact the second lecture on the same topic as part of our series. And for this discussion we have thus in our studio Dr. K.K. Arora, Associate Professor, Department of Chemistry, Zakir Hussain, Delhi College, University of Delhi. And his specialization includes organic chemistry. And let's say with this brief introduction, let us welcome sir to our studio. Thank you so much sir for coming, and I request you to begin our today's lecture.
Hello viewers, welcome to this second session on carboxylic acids. Yesterday we discussed that what are these carboxylic acids. As I discussed that they are found in many eatables, fruits, etc. Then what is the structure of carboxylic functional group, how these compounds can be synthesized, and then what are their physical properties. Today we'll start with the chemical properties. Chemical properties means those reactions where some chemical change in the structure occurs. In this we will discuss acidic nature of the carboxyl group. As these compounds are named as acids, they are acidic in nature. Then we will compare the acid strength of carboxylic acids having different substituents and maybe aliphatic or aromatic carboxylic acids. Then we will discuss that OH group, which is a part of this functional group, how does it give different reactions. Then what are the reactions due to carbonyl group, where mainly we will discuss the reduction reaction. Then the reactions in which whole of the carboxylic group is involved. These reactions mostly involve decarboxylation, and then reactions which occur in the side chain, that may be aliphatic or aromatic side chain. So we will take up these things one by one. Let us start with that carboxylic acids, as I discussed, are organic compounds that contain carboxylic group. These are some examples of basic carboxylic acids. When H is a substituent on the COH, called methanoic acid or formic acid, when it is methyl acetic acid, or ethanoic acid when it is ethyl propanoic acid. But basic functional group in all these, you see it is C double bond O, then O and H. Many carboxylic acids are known to occur in nature, and they are obtained by the oxidation of various other functional groups, because I discussed that this is the highest oxidation state of carbon in organic compound. We also discussed that physical properties of this class of compounds is due to the polar bonds which are present in it, that is a CO bond which is polar, and then OH bond which is also polar, and they exhibit dipole-dipole interactions. Then they also exhibit intermolecular hydrogen bonding, because OH has one hydrogen which is attached to highly electronegative oxygen atom. And carboxylic acids, they exist generally as dimer in solution because of the intermolecular hydrogen bonding, as this is shown here, that two carboxylic molecules are joined by the formation of hydrogen bonds. Now the carboxylic acids, as I said, that their properties can be studied under 5 different headings. 1. The reactions involving cleavage of this OH bond, and whenever OH bond cleaves, oxygen is more electronegative than hydrogen, so hydrogen will leave as H plus, and if hydrogen leaves as H plus, means it behaves as acid. So that gives rise to the acidic nature of carboxylic acids. Then second, we will take up the reactions where cleavage of this CO bond is involved. This single CO bond means the reaction where whole of the hydroxyl group is involved. So these are the reactions due to cleavage of CO bond. Then third set of reactions will be where this C double bond O is involved in the reaction. Then fourth set of reaction will be where whole of the carboxyl group is involved. Those reactions where all these atoms take part together, and then last set of reactions will be where a substitution or other reactions occur at this alkyl or aryl group to which COOH is attached. So, we will study the chemical properties under these 5 headings. You know from your previous classes that acids turn blue litmus red. The carboxylic acids also undergo this reaction, that is, they will turn blue litmus red. So, it means they show acidic nature. Now, chemically acidic nature is shown by their reaction with metals or bases. So, carboxylic acids, they react with these metals or bases, and this OH bond that undergoes cleavage, whether dissolved in water or when reacting with carboxylic bases, that is sodium hydroxide or metals. This is carboxylic acid. It undergoes dissociation when dissolved in water. This is carbon ion formed and H3O plus, means it is undergoing dissociation to give H plus ions. So, showing the acidic character. How do they react with metals? This carboxylic acid, they react with reactive metals like sodium or even potassium. Sodium salts of the acid is obtained and hydrogen is replaced from here, that is obtained as hydrogen gas. Similarly, hydrogen gas is formed when potassium metal reacts with carboxylic acids. The same reaction is shown by other reactive metals like lithium, calcium, etc. Then their reaction with bases. Any base which has a pair of electron, it will capture the hydrogen from here, and this pair of electron will go to oxygen. So, we will get the carboxylate anion, or we say the salt from here, because the positive part of this base will form the salt here, and this is the base capturing H part from here. So, any base will basically replace this hydrogen, and we will get salt from the carboxylic acid, or we say carboxylate anion. Like sodium hydroxide, H of the acid is now taken away by the hydroxide ion from sodium hydroxide. So, water is formed and sodium salt of the acid is obtained. This reaction can also be taken as a simple acid base reaction, which we call as a neutralization reaction, where salt and waters are obtained. So, sodium salt of carboxylic acids are obtained on reaction with bases like sodium hydroxide, potassium hydroxide, calcium hydroxide. Carboxylic acids are sufficiently strong acid to react with the weak bases like sodium carbonate. Carboxylic acid react with sodium carbonate, again forming the sodium salt, and here carbon dioxide is liberated. They may even react with a still weaker base, sodium hydrogen carbonate or sodium bicarbonate. They react with sodium bicarbonate, again forming the sodium salt, water and carbon dioxide. And this is the reaction that is used to distinguish carboxylic acids from other acidic functional group like phenols. Phenols are not able to react with sodium bicarbonate, although they can react with sodium hydroxide. So, this reaction goes as a test for this functional group. If you want to detect carboxyl group is present in any compound or not, so what we can do, we can treat that compound with the solution of sodium hydrogen carbonate. If effervescence occurs, that is effervescence due to formation of this carbon dioxide, it means the compound is a carboxylic acid. Carboxylic acid will form salt even with the basic gas like ammonia, and ammonium salt of the carboxylic acid is obtained. So, all these reactions, reaction with sodium hydroxide, a very strong base, weak bases like sodium carbonate, bicarbonate or ammonia, they show the acidic nature of carboxylic acids. Now, whenever a substance is acid, how strong acid it is, we compare it by the acid dissociation constant. Before studying these carboxylic acids, you have studied alcohols and phenols, and there you have studied that alcohols also have OH group, phenols also have OH group, and they show their acidic properties. So, let us compare that out of these three functional groups, which is a stronger acid and why. We can obviously compare it with the help of acid dissociation constant. Any substance, say HA, is said to be acid if it can undergo this type of dissociation to give an anion and H plus ion. Remember, it is oversimplification of the reaction. Actually, directly H plus ion will never be lost. It will be lost in presence of some solvent, that may be even water. So, just for simplification, that has been avoided, and we are writing just molecule and the ions which are obtained by its dissociation. Now, anything that stabilizes a conjugate base, that is this anionic part, makes the starting acid is more acidic. Why? A substance is acidic if it can give H plus ions. More the amount of H plus ions obtained, stronger is the acid. Now, what is the driving factor or driving force that drives this equilibrium towards this side so that more H plus ions are obtained? Obviously, the stability of the anion, because H plus ion is same from all the substances. So, more stable the anion part obtained from any compound, stronger acid it is. And this we can determine mathematically by writing this dissociation constant, we call it Ka, the acid dissociation constant, where the concentration of the anion and the proton, they are above, and here the concentration of undissociated acid is there. Now, more is the dissociation, more will be the concentration of these ions, less will be the concentration of undissociated acid, higher will be the value of Ka. So, we can directly compare by knowing the value of Ka, that more the value of Ka, stronger is the acid. Then sometimes values of Ka are very small, having some negative powers. Then in that case we use the pKa values. pKa is minus log of Ka, so that makes it a positive value. But remember that higher the Ka, stronger is the acid. Since we are taking the minus pKa, you will get the lower value. Lower the value of pKa means it will be stronger acid, because we are taking negative log it. Now, this is ethanol. Ethanol undergoes dissociation to give ethoxide ion. Here is a phenol. It undergoes dissociation to give phenoxide ion. Now, if we compare the two, in ethoxide ion, oxygen carries the negative charge. In phenoxide ion, also one oxygen atom carries the negative charge. The C2H5 group, that is the CH3CH2, is electron releasing group, and it gives more electron to the negatively charged oxygen, means it destabilizes it. Whereas in case of phenoxide ion, this negative charge is stabilized by resonance with the pi electrons of the ring. These are various resonating structures which have been shown, that negative charge is distributed over the ring and CO bond acquires a C double bond O character. And what is happening? In this way, the negative charge from the oxygen is distributed over the whole ring, means it is stabilized. So, out of the ethoxide ion or from any other alcohol, we will have alkoxide ion and phenoxide ion. We find that phenoxide ion is more stable. If anion part is more stable, as I said before, it means starting compound is a stronger acid. So, it means out of alcohol and phenol, phenol is a stronger acid. Now, let us compare it with carboxylic acid. When a carboxylic acid undergoes dissociation, we get this carboxylate anion. Here also oxygen carries the negative charge, and this negative charge is distributed by this resonating structure over another oxygen. So, there are just two resonating structures for carboxylate anion, but stabilization obtained by this resonance is more than what is obtained by the four resonating structures of phenoxide ion, because here the negative charge is distributed from one electronegative oxygen and on the other electronegative oxygen atom, where here the charge was distributed over one electronegative oxygen and then from it to four less electronegative carbon atoms. So, overall stabilization obtained here is much more. And second thing, the two resonating structures are identical. This resonating structure can be shown like this. These are the p orbitals of oxygen atoms and carbon, and a pair of electron is distributed over this like this. So what we find? We say that carboxylate anion obtained from carboxylic acids is even more stable than the phenoxide ion. So carboxylic acids are stronger acid than phenols. So we get a sequence out of these three functional groups. Carboxylic acids are strongest acid, then phenols, and then alcohols. Let us see this thing with the help of their pKa values. The pKa value for ethanol is 16, that for phenol is 10, and that for acetic acid is 4.7. And as I discussed before, that higher the pKa value, it means weaker is the acid. So this is the sequence for increasing acidity. So acetic acid is the strongest acid amongst phenol and ethanol and acetic acid. Now let us compare that if there are different substituents on a carboxylic acid, how do they affect the acidity? We have discussed that any substance which can dissociate to give anion is acid. Now let us specifically take the example. This is a carboxylic acid. It is dissolved in water. It gives the carboxylate anion and H3O+. And this is the equilibrium constant that is written for this equilibrium. And this is the Ka value, where the concentration of water, you can say, has been multiplied by this K, or we can say that concentration remains almost constant. So this is the Ka, that is the concentration of carboxylate anion into hydronium ion divided by the concentration of undissociated carboxylic acid. It is the same thing that we have seen just few slides back, where in place of carboxylate anion, A- was used. And the pKa of a carboxylic acid can be influenced by substituents on alpha carbon, largely through inductive effect and sometimes through resonance effect also. Means what will be affecting the stability of this carboxylate anion? Only this R group. So what type of substituents are here that will affect the Ka value? Let us compare. This is a carboxylate anion. Now electron withdrawing group, any group here on the carbon next to the carboxyl, if it has an electron withdrawing group, what it will do? It will withdraw this electron which is resonating over this carboxylate part, and hence it will stabilize, because if negative charge is partly removed from this part, carboxylate part, means it is stabilization. So electron withdrawing groups will stabilize it, making carboxylic acid a stronger acid. And if it is an electron donating group, means somehow this releases electron towards carboxylate anion, means it will enhance the negative charge on this portion, so that will make it less acidic, or that will reduce carboxylic acid to a weaker acid. Let us take with the help of some examples. This is formic acid, HCOH, and this is acetic acid. We know that in comparison to hydrogen, methyl group is electron releasing. So it releases electron towards the carboxylate anion that will be formed, means it will destabilize it. So it should be less acidic, and this is so. The pKa value, this is the pKa value listed here. The pKa value for formic acid is 3.8, and that for acetic acid is 4.7, indicating that formic acid is a stronger acid than acetic acid. But suppose this alkyl group is a unsaturated group, a vinyl group, means there is a pi bond here. So in these unsaturated compounds, this carbon is also sp2 hybridized, and we know that vinyl group is an electron withdrawing group. So if it withdraws electron, means this acid should be a stronger acid than formic acid, because hydrogen doesn't withdraw electron. If a group withdraws electron more than the hydrogen, should be a stronger acid. And same thing should be for benzoic acid, because phenyl ring we say is an electron withdrawing inductive effect. So, it should withdraw electron and should be more acidic than formic acid. If we compare it with the acetic acid, we find that our discussion is correct. Both these acids, this is propanoic acid or benzoic acid, have their lower pKa values than that for acetic acid. So, definitely they are stronger acid than acetic acid, but they should be stronger than formic also. It is not so. This can be explained on the basis that some resonance effect is also playing a role here, and that resonance we can explain it for benzoic acid like this, that this shows 6 carbon atoms of the ring which have their conjugation, and this is carboxylate anion having their conjugation. Now, this carbon is sp2 hybridized, and this carbon of benzene ring is also sp2 hybridized, but this carbon is attached to 2 more electronegative oxygen atoms, and this is a p orbital, this also has a p orbital. It is overlapping on this side, this is overlapping on that side, but what happens? They also overlap with each other. That is, there is an extended conjugation of this carboxylate anion with the ring pi electrons. We can show here with the help of orbital picture that this is the orbital is now overlapping with the red colored orbitals indicating for this oxygen, and the grey color orbital for this carbon, and the grey color orbital for this carbon. So, they have undergone a conjugation, and due to this type of conjugation there is a slight electron shift from the ring towards the carboxylate anion. So, it means net result is that there is some electron shift from the ring towards the carboxylate anion, hence making it a weaker acid than formic acid, but definitely a stronger acid than acetic acid. And similarly, the pi electrons of this pi bond can also take part in conjugation, and hence they also release some electron towards the carboxylate anion. Next, let us see the effect of some electronegative atom which is present, such as if you take the example of chlorine. Chlorine we know is an electron withdrawing group, and the negative charge on the carboxylate anion, that will be increasing its strength because it will take negative charge towards itself, and more is the number of chlorine groups, more is the acidic strength. We can see this thing with the help of some examples. This is 2-chloroacetic acid or ethanoic acid, and now this chlorine is electronegative, it withdraws electron towards itself. So, it means will stabilize the corresponding anion formed and should be a stronger acid in comparison to this acid, that is acetic acid. And what we find, the pK of 4.7 for acetic acid, and for this chloroacetic acid it is 2.8. So, definitely a stronger acid. If there are some alkyl groups substituted over this carbon, like we have taken here 2,2-dimethyl propanoic acid, but we can consider like all the 3 hydrogens of acetic acid have been substituted by methyl groups, and these methyl groups are electron releasing. So, there is a net electron release from this carbon towards the carboxylate anion. So, it should be a weaker acid than acetic acid, and it is found to be true. Here the pKa value is 5.1, so making it less acidic. If the number of this electron withdrawing group is more, then also they will have a combined effect and will increase the acidity. Like acetic acid, pKa value is 4.7, chloroacetic acid it is 2.8, but if there are 2 chlorine atoms, 2 hydrogens have been displaced by chlorine, the pKa value comes out to be 1.3, and if all the 3 hydrogens are replaced by chlorine, means it is trichloroacetic acid, it is a very strong acid with a pK value of 0.9, means more is the number of electron withdrawing groups, stronger is the acid. Then inductive effect, you know, it operates through sigma bonds, and if the distance between the electron withdrawing group and the carboxylate anion it increases, then its effect will decrease. We can see this with the help of this example. this is butanoic acid with a pKa value of 4.9. If there is a chlorine atom present at 2 position, that is 2 chlorobutanoic acid, its pKa value is 2.8, means strong acid. But if chlorine goes to position number 3, it is 3 chlorobutanoic acid, we find that pKa value goes to 4.1, means it is a weaker acid than this, and there is a large decrease in the acidic strength. If chlorine atom moves further, if it is 4 chlorobutanoic acid, we find that now the pKa value has gone to 4.5. Had it been a 5 carbon acid and this chlorine goes to 5th position, then its effect is almost negligible, because the inductive effect almost dies out after 4 bonds. Let us see if the electronegative atom is different. How do they affect the acidity? Like this is any halo acid. Suppose this green group is representing halogen, and these halogens are fluorine, chlorine, bromine and iodine. We find for fluoroacetic acid this pK value is 2.6. When this is chlorine, it is 2.8, because electronegativity of chlorine is less than that of fluorine. So pK is increasing, means acid strength is decreasing. If it is bromine, the value is 2.9, and if it is iodine, the value is 3.2. So as the electronegativity of this halogen atom decreases, the acidic strength also decreases, because the power to withdraw electron is decreasing. So this is the effect of different substituents and their position on carboxylic acid on the acidic strength of this. Now let us take up some aromatic carboxylic acids. This is any aromatic carboxylic acid, and obviously this will be the anion, and it might have any substituent on the ring. And if this group is represented by D, D is indicating electron donating group, means it is giving electron towards the ring, and more the electrons are given to the ring, more electrons will be shifted towards carboxylic acid, means this acid will be now weaker than simple benzoic acid. The pKa value for simple benzoic acid is 4.2. So pKa value for such substituted carboxylic acids which have an electron donating group in the ring will be more than 4.2. And if there is an electron withdrawing group, which is represented by W, anywhere in the ring, obviously it will withdraw electron, so it will stabilize the corresponding carboxylate anion more, and what will happen? It will become more acidic. So the pKa value will be less than 4.2. Let us see the pKa values of some substituted benzoic acid derivatives. Say this is benzoic acid with pKa value 4.2, and it is substituted by some group at ortho position, meta position and at para position. These are the pKa values for substituent ortho, meta and para position respectively, and here it represents the substituent. Suppose R is equal to methyl. We know that methyl is electron releasing group, and I discussed before that any electron releasing group should decrease the acidic strength, means increase the pKa value. We find that for metamethyl the pKa value is more than 4.2. For para it is even more, 4.4. Now inductive effect decreases as you move away from the source. So here this is 2 bond away, here it is 3 bond away, but still we find it is a weaker base, rather more weaker base than metamethyl. The reason for this is that methyl group releases electron not only by inductive effect, it releases electrons by hyperconjugation effect also. So when methyl group is at para position, both the effects are operating. Although the inductive effect has decreased from that of meta position, but from the para position hyperconjugation effect operates, whereas hyperconjugation effect does not operate from meta position. So that is why para substituted acid is weaker than that of meta substituted. But ortho substituent should also have maximum inductive effect and maximum hyperconjugation effect. So that should have been the weakest acid, but we find that it is stronger acid. It has pKa value of 3.9. We will come to this little later. Let us take another group, chlorine. When it is an orthochloro, metachloro and parachloro. We know that chlorine is an electron withdrawing group, and again what we find that when it is at ortho position, the acid strength is 2.9, when it is at meta position it is 3.8, and when it is at para position the value is 4. Means what we find, as halogen is going away from this carbon number 1, inductive effect is decreasing, the acidic strength is also decreasing, because chlorine increases the acidic strength by withdrawing the electrons, and more away from the carboxylate anion it is lesser electrons are withdrawn, so weaker is the acid, higher is the pK value. But we find still here that orthochloro has bit higher value for its acid strength, because there is a large difference in the pK. From 3.8 at meta position it is 2.9 at ortho position. Methoxyl group. Methoxyl group is attached through oxygen and it is electron withdrawing by the inductive effect, but electron releasing by the resonance effect. So when this group is present at the ortho position or meta position, we find the pK values are same, but when it is at para position we find that inductive effect is very little, but a resonance effect operates from here, so it is a weaker acid in comparison to that for metamethoxy, because in case of metamethoxy inductive effect is operating, but mesomeric effect or resonance effect cannot operate. But in ortho substituted, we still find that if mesomeric effect is operating, it should have been much weaker base, but it is still a stronger acid than para substituted. Nitro. Nitro is electron withdrawing group by resonance effect as well as inductive effect, and orthonitro has a pK value of 2.2, means very strong acid, whereas when nitro is at meta position it is 3.5, when it is at para position it is 3.4. The para substituted is even stronger acid, reason being because from the para position resonance effect is operative as well as inductive effect is also operating. In this discussion what we find that these ortho substituted acids are always a stronger acid whether this group substituent was electron releasing or it was electron withdrawing. This is called ortho effect. I will again repeat that it has been observed that an ortho substituted benzoic acid is more acidic than the meta or para substitute isomers. This effect does not depend on the nature of the substituent, whether the substituent is electron donating or electron withdrawing. So this was one unusual thing that was observed, and this effect was given the name as ortho effect. Now how do we explain it? We can explain it that in aromatic acids, as I shown earlier in a structure, that there is some electron shift from the ring towards the carboxylate anion, and this shift of the electron from here towards the carboxylate anion is making it weaker acid. But if somehow this conjugation between this carboxylate anion and the ring electrons, if it is prevented, then this resonance will not be possible, and the effect of the groups which are present on this ring, that is their electron releasing towards the ring, towards the carboxylate anion, will be decreased or will be prevented, and hence that will increase the acidic strength. And actually this has been observed that when any group comes at the ortho position in place of these hydrogens, then what happens, due to the repulsion between this group and the oxygen of carboxylate anion, this group takes a turn and it does not remain in the plane of the ring, it rather goes in a plane which is perpendicular to this ring. It is like this. This is the plane of the ring, and this group now carboxylate anion has gone perpendicular, and when the p orbital of this carbon and p orbital of this carbon, they are no longer parallel, the extended conjugation is not possible, So now the net electron shift from the ring towards the carboxylate anion is prevented, and hence the acidic strength increases. So whether the group at this ortho position is electron releasing or electron withdrawing, due to the steric factors is preventing the planarity of the carboxylate anion and the ring, hence making it more stronger acid, and this effect is called Ortho effect. Now let us take up the acidity of some dicarboxylic acids. Dicarboxylic acids, they dissociate because there are two carboxylic acids in two steps. The dissociation of first step is measured as pKa1, where one anion is formed, and the dissociation of second step is measured as pKa2. pKa1 for the carboxylic acid will always be lower, means first dissociation is always as a stronger acid, because when the second hydrogen has to be lost, it has to be lost from the domain of a negatively charged anion. So there will be less tendency to lose H plus ion. So second dissociation is always a weaker acid. So means second dissociation pK, that is pKa2, will have higher value and pKa1 will be lower value, and this has been observed for most of the dicarboxylic acids. There is oxalic acid, pKa1 is 1.2 whereas pKa2 is 4.2, malonic acid 2.8 and 5.7, and so on. What we find that as the number of intervening carbons between the two carboxyl group is increasing, the electron withdrawing influence of one carboxyl or other carboxyl is decreasing, and their pKa1, that is first dissociation constant, is ultimately reaching to that of acetic acid. Pymalic acid, which have 5 intervening carbons between two carboxylic groups, they dissociate just like acetic acid. But the second dissociation for any acid is always lesser, means pKa2 is higher, because second hydrogen ion has to be lost from a negatively charged species. So similar thing we can observe from aromatic dicarboxylic acids. The pKa value is 2.89 or pKa1 is 3.51, whereas pK2 is higher than this. Even for the unsaturated dicarboxylic acids, we observe the same thing. First dissociation pKa1 is lower and second is higher. So first dissociation is like a stronger acid, second like a slightly weaker acid. Then next, let us take up the reactions due to OH group of acid. In the reactions of the OH group, this is replaced by different groups, and we call that reaction as a conversion into acid derivatives. All those substances which are obtained by the replacement of OH group are called acid derivatives. This is the carboxylic acid. If this OH is displaced by chlorine, this group of compounds are called acid chlorides. If it is replaced by NH2, the group of compounds are called amides. If it is replaced by apart from some alcohol, they are called esters, and if it is another acid molecule, then they are called acid anhydrides. These are the 4 reactions where OH group of the carboxyl group is involved, and we study under the reactions of OH group. Now how acids can be converted into these functional derivatives? Let us take up these reactions. Acids can be converted into acid chloride by using the reagents like thionyl chloride, phosphorus trichloride, or phosphorus pentachloride. All these reagents will displace this OH by Cl. The best method for preparing acid chlorides from carboxylic acids is by using thionyl chloride, because the two side products which are formed are sulfur dioxide and HCl, and both are gases. So they can be easily lost, and we will get pure product if we take the calculated amount of acid and thionyl chloride. The same reactions are applicable for the aromatic acids also. Say for benzoic acid, if you want to prepare the benzoyl chloride, we can use PCl3, PCl5 or thionyl chloride, or even if you want to prepare the bromo derivative, we can use PBr3. So preparation of acid derivatives, acid halides, can be carried out by generally treating with phosphorus halides. Then amides. Carboxylic acids react with ammonia to form ammonium salts. We call them as ammonium carboxylate. These ammonium salts of the carboxylic acids on heating eliminate a water molecule and we get amides. So, we can say that amides are obtained maybe in two steps, first forming the ammonium salt and then heating, or if carboxylic acids are heated strongly under pressure in presence of ammonia, because ammonia is a gas under pressure, then we will directly get amides. Then conversion into esters. Carboxylic acids react with alcohols in presence of some acid, generally sulfuric acid is used for it, and a water molecule is lost. OH of the acid and H of the alcohol, the lost is water, and we get this group of compounds which are called esters. Esters are very useful compounds, and flavor of most of the fruits is due to different esters which are present in them. They are good smelling compounds, and many of them are used in perfumery. Some examples, this is ethanol. When it is treated with acetic acid, a water molecule is lost and we get a compound called ethyl acetate. Methanol, when treated with benzoic acid, we get an ester called methyl benzoate. I'll take up two specific examples of the esters which are very important and we are using them in our routine life. These are the esters from salicylic acid. Salicylic acid is a compound which has one hydroxyl group as phenolic group and one carboxyl group. When its ester is prepared with acetic acid, means we are preparing the ester of acetic acid using salicylic acid as the compound having OH group, and we get this compound which is named as acetyl salicylic acid, and it is used as medicine called aspirin, a very common medicine as an analgesic, antipyretic, and even for heart diseases. Then another useful compound that is obtained from salicylic acid, it is also an ester when it is treated with methanol in presence of acid. So, a water molecule is lost, O from the alcohol and OH of the acid, we get the compound called methyl salicylate. This methyl salicylate is also a very good pain relieving substance used in many balms and other pain killing medicines. Then conversion into anhydrides. Anhydrides are obtained by the loss of a water molecule between two acid molecules. The OH of the two acids, basically they lose a water molecule and then there is a linkage through oxygen. These substances are known as anhydrides. Anhydrides can be formed even by dicarboxylic acids, means if a carboxylic acid is there which has two carboxylic acids, on heating it may lose a water molecule, like succinic acid gives us succinic anhydride. Similarly, phthalic acid is an aromatic acid with two carboxyl groups at the ortho position. They are so nearly placed that on heating they lose a water molecule and we get the anhydride called phthalic anhydride. So, anhydrides are the group of compounds which are obtained by the loss of water molecule between two carboxylic acid groups. Then anhydrides can also be formed if one of the OH part of the acid is already displaced by Cl, that is we take the acid chloride, when it is treated with another molecule of acid, H of this acid and Cl of this will be lost as HCl, and obviously for that we need the help of some base like pyridine is taken here and anhydride is obtained. This goes as a pyridine hydrochloride. Then H of an acid can be displaced first as a sodium salt on treatment with some alkali and then treated with some acid chloride, then NaCl is separated down on mixing and we will get anhydride. So, these are other methods by which acids can be converted into anhydrides. Now, next we take up the reactions due to carbonyl group, and I said the main reaction due to this carbonyl group is reduction. Carboxylic acids are reduced by using the lithium aluminum hydride. Lithium aluminum hydride reduces this C double bond O into CH2 and we get primary alcohol. In yesterday session we discussed that primary alcohols on oxidation gives carboxylic acids. Now it is the reverse of that carboxylic acid on reduction by lithium aluminum hydride gives alcohols, and alcohols obtained will be primary alcohol because carboxyl group is always carbon number 1. Say this is butanoic acid, it is this carbon which is shown with the help of arrow, the CO group, that has been converted into CH2 group, that is also indicated with the help of this arrow, and we have obtained butane 1-ol. There is no change in the total number of carbon atoms. Let us take some example. Propanoic acid on reduction will give propanol 1, and benzoic acid will give benzyl alcohol. Means in this reduction reaction, the CO of the carboxylic acid is reduced into CH2. Next we take up the reactions which are due to whole of the carboxylic group, and these reactions are decarboxylations. Decarboxylation reaction means where carbon dioxide molecule is lost. Means this is any carboxylic acid. If this CO2 part is lost, H will combine with this alkyl part and we will get the alkane, and this alkane which is obtained will be having one carbon less than the starting carboxylic acid, because one carbon is lost as carbon dioxide. This decarboxylation can be carried out generally by heating the carboxylic acid with soda lime. Soda lime is mixture of sodium hydroxide and calcium oxide. When these acids are strongly heated, we get the alkane and sodium carbonate is formed. Sodium ethanoate, when it is heated with soda lime, this will be lost and the product will be methane. And the steps involved in the reaction can be shown like this, that the first step is ionization, because we are taking some alkali. Carboxylic acid will obviously in the step will form the sodium salt, and then this negatively charged oxygen, this pair of electron shifts here and this bond breaks, this pair of electron goes to corresponding carbon and carbon dioxide is lost. So we get an anion, alkyl anion or carbon ion and carbon dioxide, and this carbon ion then captures the H plus and gets converted into alkane. This mechanism is confirmed that really these steps are involved like this. It has been observed that at the beta position, that one carbon after the carboxyl group, if some electron withdrawing group is there, this decarboxylation can occur even without the help of alkali, because there is something is required to capture this H, and it has been found that this H can be taken up by the carbonyl group which is present at the beta position. So what we find that beta carboxy or beta oxy acids that is having carbonyl group at the beta position can be decarboxylated without the help of a strong base, and that can be done just by simple heating at high temperature. Now if we have a dicarboxylic acid, even the carboxyl group at the beta position can do the same thing. This hydrogen is captured by this carbonyl as it was captured here, and this pair of electron moves here and this bond breaks, and this negative charge goes to this carbon, or this goes initially as a double bond in this case, and later on by ketonol tautomerism we get a ketone, and similarly here we will get a carboxylic acid. So this confirms that if something is there to capture this H and temperature is high, this bond can easily dissociate and carbon dioxide can be lost. Then another reaction is Kolbe's electrolysis. Kolbe's electrolysis also involves the loss of a carbon dioxide molecule, but reaction occurs in this way that two molecules of carboxylic acid, when they are taken as sodium or potassium salt, on electrolysis gives an alkane after the loss of carbon dioxide from each of them. Means two molecules will combine, the total number of carbons in the final product will be 2 carbon less than the total number of carbons in starting carboxylic acids. It can be explained like this, that how this reaction occurs. When initially sodium or potassium salt of the carboxylic acid is taken, dissolved in water, it ionizes, and when electricity is passed, that is we are carrying out the electrolysis, this anion will go to anode, and at anode you know the reaction that occurs is oxidation, and in terms of electrons, oxidation involves a loss of electron. So at anode one electron is lost, we get this radical, then further it loses a molecule of carbon dioxide, we get this alkyl radical, and as soon as this alkyl radical formed, two alkyl radicals they combine to form an alkane. So this is the mechanism of Kolbe's electrolysis. And what happens at cathode? The positive part, that is Na plus, goes at cathode, captures the electron, gets converted into sodium metal which reacts with water forming sodium hydroxide and hydrogen. Means at cathode hydrogen gas will be liberated, and at anode the corresponding alkane will be liberated. If there is a dicarboxylic acid, then the Kolbe's electrolysis can be carried out in a similar way. Now what happens? Dianion will be formed, then this at anode this dianion will lose 2 electrons, we will get this di radical, then both of the position they will lose 1 carbon dioxide molecule, we will get this di radical, and now instead of combining with another molecule, a faster reaction that 2 carbons can form a bond amongst themselves, and instead of forming a cyclobutane here, a major product is ethene in this reaction. Cyclobutane is formed in very small amount. Then thermal decomposition of calcium salts. Calcium salts of carboxylic acid also on heating decompose, and 2 molecules of the acid basically, because calcium has a valency of 2+, so 2 carboxylate anions are present along with 1 calcium ion, and they lose a molecule of calcium carbonate, and say in this case a methanol is obtained, a formaldehyde is obtained. But if it is any other acid, then its calcium salt on heating will give a ketone. This can be used as a method for the preparation of ketones also, and let me explain how it occurs. Say if we have calcium propanoate, then on heating this calcium, then COO of the one acid molecule and 1 oxygen from the other, they are lost as calcium carbonate, and 1 CO and then this ethyl part they combine to give, say in this case we will get pentanone. If we take mixture of 2 acids, that is calcium salts of 2 different acids, say calcium formate and calcium a salt of any other acid, then we will get mixture of 3 products. There will be a ketone from here, there will be a product that is obtained by the combination of this part, and a combination from this. In this case this is giving us a methanol, and this is giving us some aldehyde. But if this also has some alkyl group here, we will end up with a mixture of 3 different ketones. Then another reaction is Huntsdecker reaction, that also basically involves a loss of carbon dioxide. Carboxylic acids, when they are treated with a weak base like silver oxide even, we get the silver salts of carboxylic acid, and these silver salts of carboxylic acid when treated with bromine, they lose a molecule of carbon dioxide and we get alkyl bromides. This is a method for getting alkyl bromides from carboxylic acids with 1 carbon less, and this is reaction used many times in conversions also. Then another reaction where the substitution occurs in the side chain, an important reaction for aliphatic carboxylic acids is Hell-Wohlard-Zielinski reaction. What happens when the carboxylic acids, if they have alpha hydrogen, they are treated with halogen in presence of phosphorus or phosphorus halide, this hydrogen gets substituted. Say if there is 1 alpha hydrogen in this acid, it will be substituted by the corresponding halogen. The halogen which are generally used here and give good products are chlorine and bromine. With iodine reactions are not good. Such as we have this propanoic acid, when it is treated with 1 equivalent of bromine, 1 hydrogen will be displaced and we will get alpha bromopropanoic acid or 2 bromopropanoic acid. But if we take excess of bromine, even the 2nd hydrogen can be displaced and we will get a dibromo derivative. This is shown as a general reaction. If any acid has got 2 hydrogens at the alpha position, in 2 steps both of them can be substituted and we can get di-substituted halo derivatives. Then in case of aromatic carboxylic acids, we know that COOH group is a deactivating group and it is a meta-directing group for electrophilic substitution reactions. And the common electrophilic substitution reactions are nitration, sulfonation and halogenation, and 2 others are Friedel-Crafts alkylation and acylation. Friedel-Crafts alkylation and acylation reactions are generally not shown by compounds which are less reactive than benzene, means which contain deactivating groups. So those reactions are also not very successful and good products are not obtained when benzoic acid is subjected to these reactions, but the other 3 reactions are when we carry out the nitration of benzoic acid, this is treated with concentrated nitric acid and sulfuric acid mixture, and a nitro group is introduced at the meta position. We get meta-nitro-benzoic acid. For sulfonation, we generally use concentrated sulfuric acid. but this is a substance having carboxyl group already there, less reactive than benzoic acid, so we need stronger condition, and oleum is used for this. Oleum is H2S2O7, or basically it is a solution of sulfur trioxide gas in concentrated sulfuric acid, and the benzoic acid reacts with oleum to give meta carboxybenzene sulfonic acid, means sulfonation occurs at the meta position. And similarly for halogenation, when we try to carry out the halogen in presence of some iron halide, meta halo benzoic acid is obtained. So these are different reactions which are shown by the carboxylic acids. Now let us briefly review what we have done today. Today we started that on what type of bonds the properties, chemical properties of carboxylic acids are depend and how they are grouped. We discussed the acidic nature of carboxylic acids. Then we discussed that how a substituent present affects the acidic strength. Then what are the reactions due to OH group? We found that OH group can be substituted by different other groups, and the compounds which are obtained are known as acid derivatives. They may be acid chloride, amide, anhydride and esters. We will discuss about these acid derivatives in detail in a separate session on it. Then we discuss the reaction of reduction of carboxylic acids, where carboxylic acids are reduced by lithium aluminum hydride to primary alcohols. Then they undergo decarboxylation. There are various reactions of decarboxylation. We can obtain alkanes, alkenes, or we can obtain alkyl halides. Then we discussed the substitution on the side chain, important reaction Hell-Vollard-Zielinski reaction, and then electrophilic substitution in aromatic carboxylic acids. In our next session, we will discuss about some substituted carboxylic acids, that is acids having hydroxyl group, halogen group or unsaturated acids. That's all for the today. Thank you.
Thank you so much, sir, for this very interesting presentation, and I'm sure that the students would be feeling the same. And just to tell our friends that this was the second lecture of our series in carboxylic acids, and the other one shall be following soon. And with this, I would like to take your leave, sir, and thank you again for being here. Thank you, sir, and thank you viewers for watching. Have a wonderful day ahead.